assume that you can see what I'm looking at.
We can see that, Joe. Yeah.
Great. Yeah. So this CPD is going to look at, well, as a company, we supply natural solutions for all types of construction, but we're going to specifically focus on traditional buildings and the application of the right types of insulation and what would maybe verify that it's the right type of insulation, like what justifies the selection of some of these materials. So something that's kind of becoming more and more to the forefront is things like carbon and whole life carbon assessment coming down the line. This is going to get more and more important as time proceeds. And of course, there has been changes recently to the requirements for traditional buildings and government guidance that have been published. So I'm going to really circulate around low carbon materials with kind of moisture behavior that is sympathetic to older buildings. And I give lots of case studies in this presentation just to kind of give a context to where the materials might be most useful and the broad range of applications that they actually have. What you can see really is we've been supplying a range of solutions in ecological building systems for a long time. You know, we've partnered with many of Europe's biggest manufacturers and suppliers of, you know, low energy products and low carbon solutions. For example, a lot of them that will feature today would be like diathanite, thermal plasters, or calcitherm that some people might be familiar with, to less familiar applications like, you know, natural paints and things like that. So I'm going to be kind of demonstrating that for years and years we've been supplying these products to the market, but only more recently has there been a wider agreement that this is the type of thing that's needed. These types of solutions that we've been supplying are now generally recognized as the right way to treat older buildings. So this document is hot off the press. It's latest government guidance for specifiers and installers. And it's now basically going to be, it's going to form part of the rulebook approach for improving energy efficiency in traditional buildings. So it was published in 2024 or the last quarter of 2023. And, you know, one of the key points it raises is that I took a quote directly from it, and it says, any measures that would present unacceptable hygrothermal risk should be excluded from the short list of measures. Now that's a warning to designers not to propose non-breathable applications in these types of buildings if they're likely to cause some form of decay or future detriment to the building. So the word hygrothermal features in that sense, and that's kind of a nod towards things like WUFI assessments, hygrothermal risk assessment, you know, actually looking at what the risks might be associated with dew points and condensation within buildings. So this guidance document is really useful, and it sets out approaches on how, you know, energy upgrading in traditional buildings can be achieved in the right way. So the aim should be to improve it, but without prejudice to the character of the building or any long-term deterioration. So this is obviously very important from anybody involved in energy surveying, because there's a large proportion of our housing stock and our building stock that will be considered old and traditional. And according to 2016 census records, 9% of private homes in Ireland were constructed prior to 1919, and 7% were constructed between 1919 and 1945. So most of these were solid masonry, traditional walls, but there's some examples of more modern construction like mass concrete walls, and they're typically hard to deal with as well, or thin brick walls. So it's these types of buildings that are mostly outside the scope of SR 54. And that's kind of why we've needed for a long time some agreement on how we could best approach these buildings without causing them harm or decay in the future. So to put it in a nutshell, the compatibility of new materials should be established to avoid any undesirable side effects. And what I mean by that is we're all fully aware now at this stage that the undesirable side effects of doing things like cement on older buildings has caused problems. So you put cement layers on and gypsum layers or foil face plasterboards and things like that, and you can have a moisture trapping type of effect. These old walls were always really good at getting rid of their water, you see. They were very good at getting rid of their water, but until we start surrounding them with things that prevent water from drying. So impervious cold surfaces like cements or bad drainage around buildings or high internal humidity caused by like a lack of ventilation, they can all lead to wet buildings and wet walls, okay? So TGD Part L in Appendix B provides guidance on how we can assess the impact of new materials. So we can look at new material applications in buildings through the lens of international standards. We can use EN 15026, which is a hygrothermal simulation method that takes a closer look at the insulation methods we're proposing to give you a risk assessment. So on a scale of 1 to 10, how risky is the method you're proposing? So it shouldn't just be put this up, it's grand, this is what we've done for years, because what we've done for years has led to these types of problems. So modern thermal insulation systems that have really high vapor resistivity, they can really reduce the ability for solid walls to dry out. You know, if you look at this picture here, the man is pressing a modern impervious, non-breathable insulation up against an old cold stone wall. And what's happened is he's trapped these little pockets of air behind the adhesive. And of course, the building has high humidity and it's leaking into them pockets, and it's causing this mold outbreak in the oxygen spaces between the adhesive dabs. And likewise, the dry line on the right-hand side. Dry line was always this thing where people saw it as the solution to all insulation problems. But they failed to realize that the word itself, dry line, referred to the control of internal moisture vapor, preventing it from passing through to the wall fabric where it could potentially get wet when it condenses. So they used to call them dry lines because they'd put in a plastic vapor barrier that would keep the internal moisture at bay. But what about the external moisture? What about the ground moisture? What about building decay and things that fall into disrepair over the years? There's a lot more factors that play than internal moisture. So the dry line is a very highly risky approach. And then you get this attitude whereby, oh, we can just keep it off the wall. If you keep it off the wall, you create a big space, like the spaces between the adhesive. A big space that's unventilated can be a stagnant air pocket, and a stagnant air pocket can be full of moisture. And as warm humidity leaks into that space, warm air leaks into that space, I should say, the air gets more dense. And as it gets more dense, the humidity of the air rises until it gets to the point where it falls out of the air. And you create these kind of water pockets behind insulation. So the only way to do a system like that is to fully ventilate it to the outside, which would mean perforating an old building in multiple places, top and bottom, in rows and sequences of holes. So you can do a lot of damage to a building to ventilate a dry line like that. So it's not appropriate, and it's probably not advisable to go down that road. In more traditional buildings, natural material can help. And I've shown on the screen here, I show calcium silicate, or a product that we supply called Calcitherm. But just to kind of help, you know, keep this as non-salesy as possible, lime will also do this. Okay, so what you're looking at here is a graph that's showing surface humidity, and the blue line, the blue trend line, is the uninsulated wall in the top right-hand picture, where you can see water running down the wall. An uninsulated wall can be cold enough that average internal humidity can present as condensation on the wall. And at frequent times throughout the year, that blue line is hopping above the 80% mark, whereby condensation is likely on the surface. By contrast, the red line shows that a wall, even with a thin bit of insulation on it, in this case 30 millimeters of a lime-based product like Calcitherm, when it's bonded onto that wall directly, it helps to lift the surface temperature slightly, well, actually greatly. But what that means is the humidity near the surface is never likely to get beyond the point where condensation was going to occur. Okay, so vapor closed insulations might be suitable in some instances, but you really need a hygrothermal analysis like this to determine whether or not it's risky. Now, even if condensation was going to occur on a board like this, it wouldn't really matter, because things like lime, particularly lime or lime-based products, they have a very good ability to prevent or to buffer the influences of moisture over time. So if you take a look at this image, this is me actually pouring water onto a board that's made with lime. And you can see by how capillary active it is, how unlikely condensation is to occur on that board. Because the second a droplet of water tries to form, the board or lime-based products is capable of wicking that moisture into the storage capacity of the material, where it will be held until such time as vapor pressure dictates in what direction it dries, usually back to the inside when the temperature and the ventilation is good. So boards like this can have a very high offsetting effect to the risks associated with condensation and mold. And in fact, they actually tried to make mold grow on this board in a lab in Germany for 90 days, and they couldn't get it to work, not even in a lab type context, because lime also has a high alkalinity. And a high alkalinity is naturally antiseptic, so it's quite a good biocide. And lime-based products typically do this: lime paints, lime plasters, lime-based boards, things like that. So this is why when people talk about old buildings and they mention lime, most people usually think lime, well, that sounds right for an old building, but these are the reasons why. So that's often the reason why, if you remember back in the good old days, these solutions were, very consistent with the behavior of traditional buildings and how they manage water in an ongoing fashion through the building life cycle. So back on the first image like this I showed you, it was a building covered in cement and the wall was clearly getting really wet. Well, this is why in the olden days they used to cover the buildings in lime, and they'd have good drainage on the outside and well-maintained rainwater goods and, good gravel floors and limecretes and stuff like that. Those walls were dealing with the same amount of water. They had the exact same amount of water hitting them on a daily basis, and they had the same wet lives where people were boiling pots and probably even wetter lives back in those days. But the walls were really capable of absorbing and desorbing moisture. So managing it in an ongoing way. So it's the moisture balance was right, and there was no water being trapped where it could accumulate, where in essence the cup could fill up. In this case, the cup stayed empty. It was getting wet, but it was always drying. So this is what we're looking to achieve with insulation systems suitable for use in traditional buildings. So I'm going to show you lots of cases where insulation systems can be used in traditional buildings. I brought up the calcitherm first because the first project I wanted to show you was a calcitherm project. And this is a project very dear to my heart. As you can see, that handsome fella putting on the lime plaster is myself. I'm actually doing this work on my own small project at the moment because in this space, 1968 old stone cottage, that has been inappropriately treated for years and years and years with concretes and cements and wrong types of insulations, stuff like that. I've had a terrible outbreak of mold and condensation in this building, and the air quality in the building was traumatic to say the least. So I've been monitoring with an air quality, which I'll get on to later today. And the air quality was horrendous in the building. I've had all sorts of problems in the building that have been mistreated over the years. So I finally bit the bullet and I said, okay, I keep telling people about lime-based products. I'm going to do it myself, and I'm going to actually look at the air quality in the building and see how it's actually affected it. So what I can say, it's been highly successful and no mold has returned. That's largely due to having warmer surface temperatures, but also having a better ventilation system active within the building. Some lime-based solutions can come in other forms. They're not all board-based. Take this building, for example. I mean, how could you insulate this building with a board either from the outside or from the inside? But what you're looking at there is an insulated building. So that's a lime-based insulating plaster called diatomite. And the diatomite, which some of you may be familiar with, contains cork and clay and earth and equal parts hydrated and hydraulic lime. Everything in it's completely natural, but it insulates about 25 times better than standard lime. And of course, it's CE marked, it has DOPs, it has EPDs available, and independent third-party certificate testing. So it's, all these products comply with the European product regulations and Part D of the Irish building regulations. It's nothing like, it's not a fancy mix that you do on site that you can't actually quantify. It's something that's, heavily tested and put through the ringer from a physics point of view. It can be used outside and it can be used inside. There is a range of finishes that can be applied to it. As you can see here, a good plasterer wanted a Mediterranean look on the plaster finish. I don't particularly like it, but they loved it in the building. Apparently this is quite popular in some parts of the world, but it can be done in a very traditional way where you have rounded reveals and stuff like that, or it can be done in a very contemporary way. This building is done both on the outside and the inside with that same product, and it's a protected structure. So very little in terms of the material palette is suitable or appropriate for a building like this. Imagine trying to explain to the homeowner that they should put XPS boards up against this building, or a dry lining system internally. You'd lose every feature in the building. Look at the top right image where the radiator is and the window shutter boxes and the ornate detailing and large skirting boards and stuff like that. How do you deal with all that with any type of heavy frame system or bonded board based system with angles and stuff like that? But you can do it quite easily with a plaster that can be applied and squeezed into the right positions. Here's another case study in Burren Street in Carlow by the architect Ken Anderson of Holly Park Studio, and a guy called Alan Dillon, really good plastered this building. But you, at first glance, you would not know that this building has been insulated, but it has been. They actually removed an inappropriate cement plaster that had caused the original roof to completely decay. It caused all kinds of problems, chimneys cracking and stuff like that. So they ended up having to re-roof this building, and it's an important building. Daniel O'Connell apparently stayed here during elections, but you'll notice that it's joined on to a neighboring property and it's on a roadside, and there's just not much you can do with a building like this. So what they done was they took off the cement that caused all the problems. They left alone their lovely windowsills. They didn't move the positions of them at all. They didn't have to do anything clever with footpaths or anything like that, or drainage positions. They took off 30 mil of cement and they put back on 30 mil of diatomite, insulating thermal plaster. And on the inside, they removed modern gypsum plaster and they put on 40 mil of diatomite. So they ended up with a 70 mil insulation strategy, but the building helped to maintain its character. And it's performing very well. And that picture was taken pretty much when the job was done, but the next picture was taken 4 years after. And it looks as good today as it did the day it was done. I went to this job just kind of accidentally. I was down looking at a different project in Carlow and I couldn't help myself. So I walked down the street and I found the job because I'd done all the calculations and stuff for it. And I was down rubbing the walls when the woman who owned the house pulled in. That's her black car outside the house. And she, excuse me, what are you doing rubbing my walls? And then I just had to kind of explain to her who I was. And that was her chance to tackle me and say, oh, this stuff didn't work or whatever. But she was offering me in for dinner and told me her sons love playing guitar up in the upstairs rooms because it's had a kind of an effect where it's protecting them from overheating and stuff like that as well. So it's been really, really successful and really, really, high quality insulation at the end of the day. Now, it may not break any U value records. Her U values in her case were something like 0.45, but still highly advantageous in so many ways and much, much better than the wall was originally. Products like this can be used in complicated examples. Here's a project in Cork. Without naming the project, you'll see it's quite a fantastic example of maybe the versatility of something like this, where you have difficult dimensions to deal with and complex geometries. And again, you can't put a dry line in here. You obviously can't insulate the building from the outside. So, this is Ken Sisk plastering, applying the product using a plaster pump that will be applied very, very quickly in multiple layers, day after day after day. And all he's putting on the wall is lime, cork, clay, diatomaceous earth, and he'll do it in multiple layers until the desired thickness is achieved. And basically what they do is they'll work between reference bands, which you can see he's positioned on the wall so that he can get a consistent depth everywhere. He'll just work between those and he'll screed off between them. And he'll reduce his depths going into reveals. And then when it's all cured and screeded off, they'll put a nice fine white line finish on it, like you can see in the right-hand image. And this is pretty standard approach to an insulating plaster project like that. And it can be scaled up to massive projects like this, where really other options just aren't there. Like you couldn't alter the character of a building like this by putting in rectangular boards. This is Abbeyside Church restoration in Dungarvan. Nearly 100 mil of thermal plaster was used in this case, but you would never even notice the building was insulated physically or aesthetically. But when you walk into that building and the 8 radiators, you can see one of them in the middle picture. There's 8 of those in that building to heat that building, and that building is warm when you walk into it. And the second thing I noticed in that building when I walk into it is the acoustics are like no church I've ever been in. It's got quite a good noise reduction coefficient. That's not something that was planned in this case, but it's something that's quite noticeable. It's a very soft sound in that church. If anyone's ever down there, go on in and take a look. So that's just to give you an idea. This was it while it was going on, and you can still create edges using arch beads and things like that. But ultimately, when it's finished and painted with a nice breathable paint, you end up with a church that looks like a church, but it's been very well insulated, contrary to other ways of doing things. So board-based systems can be used in multiple applications. Here's Muckross House. The architect in this job was Brendan Cormacan, and they had issues where parts of the building could not be insulated, like stone walls and stuff like that. So having a wet plaster can be used in a kind of a versatile way where you can do between things and up to things, and you can reduce depth and you can taper off to existing features and stuff like that. You can still end up with most of the building insulated where otherwise you just wouldn't have had any options because it's too complicated to put in anything else. So that's a lime-based system, but a lot of bio-based materials like wood fiber or cork or straw, they share many of the same benefits as the lime-based systems, and actually most of them are recommended to be applied onto lime or finished with lime. So in this case, I'm showing a product called Gutex Thermo Room, which is a wood fiber board and insulating board but it's bonded onto a lime background, which has to be straight and level. You can see in the bottom left hand end of the image, that was how they prepared the wall with lime. And then the wood fiber is bonded onto the wall, and then it's finished with a lime finish on top of it. So it kind of traps the biogenic board between two lime surfaces, and it gives you all the breathable advantages of both products, and completely compatible and consistent with, you know, the messaging, most current guidance. So, as I said before, they're typically finished with lime, and they've been used in many successful projects, including, in this case, this was a project in state care, and it's a very high profile project. But they used, on the top left hand image, what you're looking at is thermal plaster finished with the lime skin, and on the bottom left hand image, on the other side of the building, they used wood fiber. And the reason they want to do that is they're currently analyzing both sides with in situ moisture and thermal monitors. So they're going to try and, you know, publish documents that will lead to better guidance for specifiers, you know, looking after buildings and state care and things like that. So it's important. I should point out that in situ monitoring of U values is being promoted heavily in protected structures and buildings of interest, but where they're, you know, undertaken, they should be done in accordance with IS 9867. But in the absence of acceptance of that standard by the European Commission at the moment, in situ U values are currently not acceptable source of data for demonstrating compliance with TGD Part L in BER calculations, which I think is very frustrating. But until they get some sort of agreement on 9867, that's the way it is. But it's still being recognised and still being promoted as a more accurate way to reflect the U value of old walls, particularly where, you know, Part L requirements don't apply, but buildings that are exempt, like protected structures. So wood fiber is really useful insulation, and people kind of have a mindset thinking that it's often used like in modern new build construction or timber frame construction, and that's true. But sometimes this can form part of a retrofit. So while it is true that you're seeing wood fibers more and more in like modular construction, like this project, which is a like modern method of construction by Activo, where they're applying it as a secondary insulation to the outside of modular units, you are seeing in some cases where modern methods of construction are being used in combination with older buildings. What I'm looking at here is a low carbon construction technique called CLT, cross-laminated timber, being used as an extension off the back of a mid-terrace Edwardian building in Dublin, a 4-story Edwardian building in Dublin. So it's actually a modern method of construction being bolted on to the back of an old brick building. And in that case, you know, this building has similar requirements to older buildings. Timber needs to breathe, it shouldn't be getting wet, etc., etc. So we do supply membranes which can form the airtight layer. They're helped to protect the product during the wetting phase or the construction phase. But as a company, we also supply the calculations and the recommendations required for the engineered fixings that are necessary to mechanically fasten the wood fibers into position. And as I said, like that's quite important that as a supplier, we're not just selling products. It's important to note that we do offer these technical services as well, because it's important that they're installed well, because that's why products get a bad name. Products don't fail people, people fail material. That's generally might be a bit cheesy, but it's also very true. So we have quite a detailed technical backup as a company, and you know, people that we work with on projects would generally lean on us quite a bit. But wood fiber, its versatility is well known, but sometimes what you might notice, particularly if you're surveying a building or something like that, is you mightn't often see the opportunities to insulate an older building. But here's a prime example of that. Here's the Rubric building roof. It's the oldest building in Trinity campus. And since the 17th century, this building has had no insulation on its roof. So therefore, when the heating is turned on inside, I guess if you had a big enough thermal imaging camera and you were upstairs looking down at it, you would see a lot of heat loss through the roof. But wood fiber, being compatible with timber from a conservation point of view, there's nothing more like for like than timber with timber. So it's a prime opportunity for old roofs to insulate them from above. Throw a blanket of insulation up over the roof, insulate into your rafters and create an airtight line inside. That's how you thermally refurbish an old roof, and do it in a protection type way. So that actual product is also very weather durable and it offers another layer of protection under old slates and things like that in the event of a roof leak over time. So it'll help keep the building warm, yes, but it'll also help keep the building dry long into the future. And it's essential that we bring these buildings into, modern standards. Otherwise, they're going to be too difficult to heat. Likewise, a building like that, using natural materials opens more opportunities to insulate them in general. What you're looking at here is the facade, or one facade of the rubric building, the same building, where diatomite was used on the first 3 floors to insulate the building from the outside. And you can see in the close-up of the wall to the window that they use 2 finishes. In the reveal, that's called a rubbed-up finish, where they finished it nice and flat into the old lovely sash windows. And on the surface, they used a lime harling over the diatomite, so they could get a consistent finish with how it would have originally been harled back when the building was built quite a long time ago. So that building is actually quite well insulated. Believe it or not, you don't really notice it because it just looks historically accurate. And the only reason the upper floors are not insulated with the same thermoplaster is historically they never had a plaster on it. So from a conservation permission point of view, it wasn't acceptable. But this building also used clever airtight taping and wind-tight taping in the reveals. You can't see it because it was pinched nicely between the plaster and the frames. But draft proofing in this building was a key focus because from a retrofit point of view, airtightness is not just for new builds. But while it is recognised that airtightness is probably very useful in new builds, and it's often kind of seen as maybe one of the key indicators of a high-quality passive house. For example, LOETB have training centres, the National Construction Centre, where they, show people how to do airtight detailing to the highest possible standard. And you'll see this type of airtight detailing taking place across the most airtight passive houses in the country, and even the NZ Centre of Excellence in Wexford and stuff like that. But in reality, airtightness is not just for new builds. Airtightness is also for older buildings, okay? And what's often overlooked, and this is actually coming from that energy efficiency in traditional buildings guidance booklet that's been published. What's often overlooked is the necessity for airtightness to prevent the movement of moist air through convection, which is basically air moving through the building fabric or at junctions between elements, and that can lead to condensation risk. So in this image, what you're looking at, that green membrane that's kind of over and between the rafters, that's a retrofit membrane. And in the bottom position, underneath the insulation, it's more vapor tight because it's in a warmer area. But in the top position where it crosses over the top of a rafter, it's more vapor open, so that if any vapor does get in there, it can escape through it. These are retrofit membranes that can be used to kind of cradle insulation between the rafters when being insulated from above. But contrary to popular belief, leaky construction is not a feature of traditional buildings. This is debunking that myth. It's a consequence of the longevity of the building. And basically, buildings get more leaky due to shrinkage and settlement, repairs, wetting, drying over the years, over the lifetime of a building. But that's all led to unintended cracks and creating airflow pathways that people would have thought were design intentions. They were never intended to be leaky buildings. In fact, there's a lot of data out there that shows buildings built in the 19th century are as airtight as buildings built in the mid-90s and the mid-2000s. There's a lot of data to show that they just got more leaky over time. So traditional construction can really achieve high levels of airtightness without danger to the building fabric. In fact, if you have breathable materials such as wet lime plaster or diatomite, you can achieve very high levels of airtightness with that type of product, because although vapor can move through it, air cannot move through it. Vapor is a much different animal than air, but it's completely draft proof. So that'll therefore reduce the risk of condensation from occurring. And even in the old application of lime washes, which would have been like ritualized in most rural communities, that was an effective way of reinforcing an external airtight layer. So if you had a lime wash that was redone periodically, you'd make the building more wind tight just by doing it periodically on old traditional Irish cottages. So this concept that airtightness is not for old buildings is absolutely false. And just to prove it, here's Ivy House, the Department of Foreign Affairs, where they took a similar strategy, retrofitting the roof, putting in an airtight vapor control layer before insulation was placed in. Here's a protected structure railway house by Cooney Architects, McKelvey Construction in Ballinamore, where a similar approach was taken. And you'll notice it's quite simple and quite straightforward. Here's Shankill Church in Lurgan. I think I have a small video just to kind of give you an idea of the scale. But again, just like people would have thought, you can't insulate these roofs, but you can. So as you can see, it's quite a massive scale, but you can see them fitting a flexible wood fiber insulation, tightly packed between the old timber rafters without disturbing the existing lath and lime ceilings below them, because the membrane is in position, cradling the insulation and preventing any forces on the existing ceilings. So air tightness is not just for new builds, it's for all buildings. And here, without naming the man, it's quite an important politician that most people would love. And this was his house in the centre of Dublin, and this is his roof. And as you can see, he's also taken the opportunity to retrofit little bits of airtight membrane between existing ceiling joists on a flat roof detail before applying a flexible wood fibre between the ceiling joists and leaving a ventilation space to create a traditional cold roof. So they took the opportunity because the building was so old, so big and so leaky that while they have a chance to restore part of the roof, they're going to take it. And there's a really, really good roofer here called Jamie O'Driscoll that carried out the work to extraordinary standard. But again, it's only to go back to, while high quality airtight detailing like this timber frame by Shoalwater is often the indicator that it's going to be a good airtight building. In fact, airtightness is not just for new builds, and the skills are out there to do it. Like there's a lot of training available in Ireland for people to do airtightness, but airtightness is really easy. The skills are not lacking in this area, and general awareness around the vital role that airtightness plays in all construction has grown, even in traditional buildings. They make the point about airtightness because it's really key then to think, well, if the building is going to be more airtight, more energy efficient as a result, you really do need to be a little bit aware of the critical role that air movement is going to play in the building. Okay, so controlling humidity at source lets us build more capacity into our overall insulation strategy. So most fabric retrofit measures reduce natural ventilation, and that leads to poor indoor air quality and increased moisture buildup. So the more you do in a building, the more likely it is that this is going to occur. Ventilation is defined as the purposeful supply of fresh outside air and the removal of stale indoor air to or from conditioned spaces within a building. So the ventilation might be provided by natural or mechanical means, and it's characterized by controlled exchange of air as opposed to uncontrolled leakage. So in this building here, you can see in this image, the issue here is that they have what they think is a naturally ventilated wall. So they have a hole in the wall, but they've got terrible problems with indoor air quality because it's evident by the mold growing on the ceiling. So that mold is only growing because the internal conditions are bad enough that the conditions needed for mold can thrive. This is being caused by unplanned air leakage or a lack of air change in the building. So as a company, we supply a decentralized system that can be useful from a retrofit context. I'm not going to get into it too much today, it's for another day, but whole building decentralized ventilation can cross-ventilate entire spaces if they're planned correctly. And just to give you a little idea, here's a fluid dynamics program that kind of demonstrates how they work. They work in push-pull fashion, where one fan is pushing air into a building while the other fan is pulling air out. The one that's pulling air out is pulling out warm, stale air. So it's important that that warm, stale air is passing through a heat exchanger. And then after 70 seconds, you'll notice under the doors where the door cuts are, you'll notice that airflow direction changes. Now that air that was being pulled out, the warm air from the left-hand side, that fan is now pulling in cool air across the pre-warmed heat exchanger, delivering heat recovery to the building while also mixing the air or diluting the potentially stale air within the building. So this is a very simple plan, but just to give you an idea of how push-pull systems actually work, they're always planned in pairs. And to give you an idea of what the main fan looks like, you can see one there on the left-hand side. That's a decentralized heat recovery fan. And then if used in isolation on its own, it could technically be called a single room heat recovery ventilator. But when used in a pair, it's more accurate to describe this as a push-pull system where things between get cross-ventilated. And in bathrooms, you just use classic extract, demand-controlled, humidity sensitive, light sensitive, odor sensitive, things like that. And then if you plan it correctly in pairs, there's nothing to stop you doing it for more complex spaces, because it's really still just a matter of positioning fans in the right place so that everything in between gets air and air change. So air quality in buildings is hugely important. And I mentioned my own project at the start, and I mentioned how I've been looking at air quality in my own project, because I have evidence of poor air quality everywhere, mold, condensation, etc. So I've been monitoring it myself with little handy air quality monitors, and that's, I'm collecting data, and I want to know what the level of harmful pollutants are within my environment. So indoor air can be 5 times more polluted than outdoor air, and it's between 200 and 500 times more likely to carry carcinogens like radon. Okay, so that's like huge. So your internal environment can have a real bad effect on your health or a good effect on your health. You want to be surrounded by fresh air in the same way as you want to drink fresh water. You wouldn't drink dirty water, but we've been breathing dirty air for years. So there are, numbers of commercial monitors on the market, but they usually all look at the same things. They look at temperature, humidity. Some of them look at particulate matter, carbon dioxide, ozone, nitrous, etc., etc. So radon being another one, but it's recommended that if you want to do like something quite scientific, you need to look at post-retrofit, pre-retrofit air quality as a way of measuring your success or failure. So what I've done is I've taken a look at post-retrofit air quality, shocking bad, and then I've taken a look at the measures that I've put in and how they've influenced the space. And in my case, I want to look at two things as being a useful indication of air quality. I'm looking at humidity and carbon in my air, because carbon and humidity are generally generated by people's activities inside. So the more people you have in a space, the higher those metrics will be. And the better ventilated your space will be, the more controlled it will be. So in this case, what I've put up on the screen is just the air quality metrics that I'm looking at, parts per million of carbon in the air. You see the little red spike on the left-hand side, and humidity in the air. And notice that the spike happens at both at the same time. In this project, when 9 people were in the sitting room having a chat and drinking tea, both the parts per million of carbon in the air and the humidity in the space was rising above acceptable levels, nearly 2,000 parts per million of carbon in the air, which over time wouldn't be a nice atmosphere to be in. And the humidity had risen to around 60%, where it was actually much lower than that because it's in a very, very warm environment with a stove going. But the ventilation system that I put in, when it was activated and it was put into ventilation mode, you can see the way the carbon drops consistently over the next hour and the way the humidity drops in tandem with it. So the ventilation system in this case is proving to be adequate and effective in my buildings. So it is important that we're doing retrofits. We do understand a little bit about the air quality and the effects the materials can have and our applications, whether they're accessible or not. So just to kind of come back to the installations again, you can play around with these materials and sometimes they might be useful in ways you're not expecting. So, and here's a job in Kilrush, and it's a really interesting building that belonged to the Vandeleur family back in the 1830s. And this building has been handed down for the last 2 centuries through a medical family. They I think there was they used to sell drugs, but not like drug dealers. They were back in the day, they used to sell pharmaceutical drugs from the front sitting room window, and it's been passed through doctor to doctor to doctor for 2 centuries. And I think one of the last people that lived in this building was he was the basis of some movie played by Michael Caine. He was in some World War II mission where he bombed a dam, and he was a guy that lived in this house. It's a very important building. What's his name? I can't think of his name, but he, so it's a really, really interesting building. Michael Keating was the architect on this one, but they had a lot of challenges. This building here, they wanted this little projecting staircase off the back of the building, they wanted to keep the inside of that exposed stone, but yet they were insulating all of their building from the inside with calcitherm. So the problem was that to keep that with exposed stone inside, they're going to have to accept this big thermal bridge in that area and a lot of heat loss. So diatonite, in combination with calcitherm being used inside, diatonite was used to insulate the projecting part of the building, which you can see on the right-hand side, where it's just getting some color samples put on it. So they actually insulated around the outside of that without changing the aspect of the building at all. And then they proceeded to continue with the calcitherm on the inside of the rest of the building, the calcium silicate lime board, which you can kind of see here. Now, they accepted loads of compromises and thermal bridges because they wanted to expose some of the stone in the area. These products are quite versatile and they help to offset the risk of issues occurring with condensation and mold. The diatonite comes in many forms. Some of the forms it comes in can be used in very saline environments. So you might have coastal projects where people are concerned about the use of any plasters in them environments because of the high salt content. But there are products in the range that are suitable for use in even these really severe situations. Which you can see in this case, when the man looks out his door, he's practically in the sea when the tide is in. So in this case, the Atomite was used, and that's holding up really well. Natural materials can have lots of advantages. For example, their reaction to fire, Class A1 non-combustible, and that's why it was used very successfully in the Primark building. You can see Calci-Therm was applied in the restoration and upgrade of the Primark building. And they multi-layered it in this case because building regulations called for quite an onerous U value. And the architect was Hallback and Douglas and JCA in that job. But yeah, it was really, really successful. And then if anyone's ever in the building, the only place you'll actually see Calci-Therm because of all the shop fit out is up near the clock on the very top floor. What you're looking at surrounding that clock is actually Calci-Therm. So it's the only place in the entire building where it's visible, but the entire building was done with calcium silicate. So natural installations can sometimes be a bit of a surprise. In this case, you kind of see rectangular panels. Sometimes you see them in McDonald's or restaurants and stuff like that. But they have a lot of good sound properties because they have unique textures, large surface areas. So in this case, they use wood wool boarding that's bound together with mineral dust like lime. And it can be used to insulate, it can be used to plaster over with limes, or can be left exposed for acoustic absorption, which is why it's used in sports halls and schools. For example, in this case, it was a Gale Skull in Limerick by Thompson Architects that had used it. And yeah, so you may see this out there and just wondering what it is. It was very popular back in the day. People used to think it was straw board. Sometimes it's called straw board, but the correct term for it is wood wool. So wood wool paneling is basically like modern equivalent to riven lath. Something that you could really plaster very easily because of its texture. So surface this, I'd put up this image because in this image, what you're looking at is an old courthouse, right? And in this old courthouse, you can kind of see on the bottom floor, there's quite a lot of moisture that's kind of still evident in the wall. But the more they picked off that cement, the drier that building got. And there's kind of a lesson in this because there was a lot of diagnosis of rising damp in this building, and that's just inaccurately diagnosed. Surface condensation is often mistaken for rising damp, and the resolution to those two things is very different. So it's really important to make sure you know what is actually present before recommending any remediation. So surface condensation can account for 90% of dampness found at the base of walls in traditional buildings. That's like a very key thing to be aware of. I wouldn't just jump to the rising damp conclusion because you may end up doing things like tanking or chemical injection wrongfully on old buildings and causing harm to the product or the project. So before I move on to the final case study, I'm just going to make a quick point on paints. All these products that I mentioned today are suitable for use in older buildings. There's very little point in using them if a plastic-based paint is applied on top of it because it will limit its breathable qualities. So just to make you aware that breathable paints are available that comply with even the strictest air quality standards in buildings, like the Well Building Standard. So I'm not going to dwell on that again. It's just to make a point that there's no point in putting a plastic film forming paint on top of a nice breathable lime finish. So I'm going to wrap up with a stable conversion project in Killarney, County Kerry by an architect called Sean McGillicuddy, and Ned O'Shea Builders and Sons were the guys who done this project. And what I like about this project is they took it from this state to an A2. Okay, so they brought it an old stable that really, you'd need to look through what it looked like at the start to really notice what you could do with it. But the architect had a desire to do this in a low carbon way. And he had a client that was equally as optimistic to do the same thing. And they wanted to bring it to modern living standards, but they wanted to do it in as ecologically as sound a way as they could, while still having a nice, comfortable space to live in at the end. Okay, so it's a former stables that housed prize-winning horses in Kerry, and it was really structurally unsound. They had no perimeter drainage, and there was a lot of decay to this old barn over the years. To make matters worse, they found bats on the site, so they ended up having to halt the project for a little while and get Batman in with his little silk bags, and that's him picking them out of the ivy. They were all asleep as he was doing it. I just happened to be there. I was really lucky. I was down there visiting with the architect when this was occurring, so I got to just kind of chill out and look at what they were doing for a while. But they were taking the little bats out from behind the ivy, and there was about 20 of them, and they had to create this little bat cave for them. You see it on the bottom right image. They had to build that on site. and had to put up this kind of slippy panel. If anything tried to climb on that, like a ferret or something, it would just slip off it to the entrance. But they rehoused the bat inside that, and then they had to plant all these willow trees in 2 lines towards its habitat, because the bats apparently feed in that kind of cluster of trees. So they had to try and direct them into their new house, and hopefully they would accept it. But apparently it was very successful and let them get on with the job. So they've done it the right way, and then they got off to a better start. They didn't want to change the dimensions of the building too much, and really they couldn't. So they used the existing floor plan of and you can see in the ground floor with the small rear extension. The rear extension was actually just made from block, but they put a roof with Gutex insulation on top of it, and they insulated into the roof in that area with natural fiber insulation and made it airtight from the inside. But the rest of the building is the same. It's just same old barn, but they cut a big hole through the south-facing aspect to make the most of the view there. You see the kind of big sliding door that they have in the kind of kitchen diner. And then to make some more space to sleep in, they actually just built a timber frame construction onto the top. So you see the first floor mezzanine with the small roof extension. They built that onto the top of the old barn, and that's what it looked like from above. So it's a timber frame, low carbon extension moving upward, but still keeping the same type of dimensions within the building. And that was done with natural fiber insulation, wood fibers on the outside, wood fibers across the roof, airtight membranes, and it's finished inside with wood fiber finished with lime, is what you're looking at in the bottom right hand image. So this is an idea of how they built those timber frame walls and how they insulated the old stone walls from the inside. So you can see in the top right pixel, you can see that they put a background layer of insulating plaster against the old stone wall, and they followed it with a 60mm wood fiber board coated with a lime finish and breathable paint. On the roof, they put wood fiber board over the rafter, wood fiber board in the rafter, and airtight membranes underneath the rafter to seal the building airtightly. There was some challenges, of course, which I'm not going to get into too much, but some of the structural repairs required concrete. And what you're seeing here is the green colouring on the concrete was a grip primer that was applied to allow the thermal plaster to continue from old stone walls into concrete areas where it could just maybe be a continuation of the insulation strategy. You're looking at some clever detailing there on the roof. Counterbattens were applied. That's to give a large amount of ventilation underneath the slate, to make sure that any vapor that does get in there is dealt with by the wind accordingly. And what you're looking at on the top right hand image is how they cut through the old stone wall with a rail saw to make use of that view, which is fantastic. Where it's actually pointing is one of probably the best views in Ireland. But they insulated their floor with limecrete screed on top of foam glass gravel. So you can see a little bit of the suggestion of foam glass gravel in the top right image underneath the geotextile membrane. And then you can see the geotextile membrane had a lime applied onto it. And then there's a little perimeter of cork board applied against the thermal plaster in preparation for the wood fiber, which will be applied later to the wall. Now, I wasn't there when the wood fiber was being applied, but a good friend of mine who might actually be in attendance today, Daniel Keenan, would be a colleague of you guys.
Fantastic, Joe.
Daniel would be very versatile in this area, and he'd be very fluent in the use of
case studies,
low impact materials and older buildings. But he practices what he preaches too. He actually bought an old cottage,
Ollie had to pop away there
doing it up himself. And so I've used these images and I've inserted them into that other case study, because it's exactly what they done in that other case study.
Fantastic, Joe.
Daniel leveled his walls with thermal plaster, which you can see in the top left image, before applying wood fiber boards and doing some nice airtight detailing at that stage onto the thermal plaster before finishing everything with nice lime in a very traditional way. So you can see that it's very practical and very easy to achieve, but also very highly appropriate in the right context, whether it's in Kerry or in County Longford. But when the project was finished, the client in this case might be quite a litigious person. They're involved in law at a very, very high level. And they are reporting that they're living in a really, really nice house. But the most important thing was just with a heat pump and with the right windows, with the right levels of moderate amount of insulation in the right places, they got an A2. So, that's quite a considerable upgrade for a building like that. And it's probably my favorite retrofit at the moment that I've worked on, because it just shows that it is absolutely appropriate to tackle a building in this way. But I don't know how I am for time, guys. I think I'm pretty close to the time, but that's the end of the presentation. So yeah, I hope that was interesting.